Thank you. Great. So welcome. This is my name is Ifan Stephens. Some of you might be familiar with me because I gave a lecture a few weeks ago on kinetics. So today I'm going to be talking about combining experiments and theory from an experimentalist perspective. I think first I'll have some quotations. I'd like you to guess who actually said this quotation. So the first one is it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. So I don't know if how many of you agree with this? With this? Is anyone hands up if you agree with this proposal? Otherwise, if any of you online disagree, please let me know if you have any opinions on this. So one person agrees. And none agrees as well. Does anyone disagree? Sorry, you disagree. So Jesus disagrees. Why do you disagree? Yeah, there's a lot of different ways, but I think actually as an experimentalist, I disagree with this statement. So does anyone know who this statement was from, by the way, as well? I'm just checking my messages. Does anyone know? So it's from Richard Feynman, Nobel Prize winner. Oh no, hold on. Whoops, sorry. I'm just trying to transfer to. No, it doesn't matter. So if anyone sends a message, let me know because I was trying to set it up on my laptop, it didn't work. So I disagree with this statement because the thing is actually, as an experimentalist, often experiments are completely wrong. They often get things really, they're not done correctly. There's a lot of different interpretations of experiments. And this is not always a valid statement. So I guess experiment theory should agree with a well-done experiment. A lot of experiments are not done very well. I'll be showing examples of these later. So another experience I had once at a conference in the MRS meeting about 10 years ago, and I was in a bit of a rush, and I was giving a talk very quickly. I wanted to show maximum amounts of results, which is not always a good idea. I only had a 10-minute talk. Another well-known scientist told me, "Great data, Ifan, but I'm awfully confused. You mix experiments and theory when in reality they're just fact and fiction." So I guess what they were suggesting was that theory is fiction and experiments is fact. Again, I'm not sure if I completely agree with this statement because, like I said, the experiment can often be wrong. So I think just to give a little bit more insight, my own, I'm an experimentalist, already mentioned, but I spent a long time at the Technical University of Denmark. And there first as a postdoc, and then I became a member of academic staff there. And what was interesting there was actually I was first based in a corridor full of theoreticians. There were only 3 of us who were experimentalists. So I was surrounded by theoreticians, and we didn't even have a proper lab. We just had a converted office, actually. So it was really good for actually building up a relationship with theorists because we built up a lot of trust. We were constantly discussing things, and I think that's really the way it has to work. So I think that if you really want to get meaningful results out of theory, that you need to speak to the theorists on a very, very regular basis. You can't just come along and say, "Okay, can you explain my data?" and expect a coherent answer. And at the same time, for theorists, you can't expect an experimentalist to prove their predictions unless you really kind of understand, somehow meet each other halfway. So this is a list of different theorists I've collaborated with. It's not extensive. In particular, the groups of Jens Nørskov and Jan Rosmeister, who are at my former institution, the Technical University of Denmark. And so today what I'm going to be talking about in scope is specifically relating experiments specifically on my own area of research, which is catalysts for electrochemical devices or electrocatalysts, to density functional theory calculations. So I'm not going to be explaining the underlying theory. Clotilde will be discussing this next week. And it is, I admit, quite specific. I'm not trying to, it's quite personal and it's very much based on my research, but I guess what I'm trying to show is examples where you can actually, well, at least I think you can actually marry experiments and theory in a way that I think is convincing, even though I always appreciate there might be other interpretations, because I'm not a particularly big fan of when you have experiments and theory and they seem to match, but actually both are pretty much nonsense. So I think that the important thing to bear in mind when you're doing electrochemical experiments, there's a very low barrier to getting data. And it's the same when I think, as far as I understand, it's not actually that difficult to do a DFT calculation. But actually, to do a meaningful DFT calculation, I think is more difficult. It's the same to do a meaningful experiment is often not that tricky. But because there's such a low barrier to entry to both electrochemical experiments and doing DFT, that we have a lot of rubbish in the literature. And it's important not to take things at face value sometimes if you really want to get some insight from your experiments and theory in combination with each other. So I'm going to be talking about 3 specific reactions I've studied, I'm studying from my research. First, oxygen reduction to water for fuel cells, then oxygen reduction to hydrogen peroxide, and then what I've been doing a lot more recently, nitrogen reduction to ammonia. So, as you know, many of you will be aware that polymer electrolyte membrane fuel cell operates. You get the energy out of reacting hydrogen and oxygen and harness it in a controlled way. So you have hydrogen oxidation happening at the anode and oxygen reduction happening at the cathode. So a big advantage of this has got longer driving range than lithium-ion batteries, particularly good for if you want to look at heavy vehicles, and it's got a very short refueling time. So obviously, when you look at an actual fuel cell, it's quite complex. It's quite difficult to actually do measurements on a real fuel cell because it's difficult to optimize, especially in an academic lab. And what I'd like to point out is actually you need a lot more platinum catalyst to drive oxygen reduction than you need for hydrogen oxidation. And that's because oxygen reduction is intrinsically more difficult to catalyze. I'll be explaining that why in a moment. So ideally what we do, and maybe there's something we'll do in the future, we'd be doing all our measurements in an actual fuel cell and then and being able to relate our measurements on a fuel cell to first principles calculation in a trivial way, but it's not actually that easy to do that. So usually we're trying to look at more model surfaces, and what I usually find they're easier to relate to theoretical calculations. So we look at things like well-defined nanoparticles, well-defined thin films, and well-defined even single crystals. So a single crystal is, in this case, it's a platinum single crystal. It's 5 millimeters in diameter. It's been annealed to expose one surface orientation, and we test it under model conditions. So usually a liquid electrolyte. And ideally we go through an iterative loop, looking collaborating with theorists, synthetic chemists, people doing characterization, electrochemical testing, and try to enlighten each other on our different specialities, so we can get more insight. It doesn't always work out. This is what we aim for. So the simplest system you can actually look at in terms of experiments, and this is the easiest one to relate to theoretical calculations, is platinum 111. So it's a closely packed surface of platinum. Like I said, you have a disc that's 5 millimeters across. You put it into a shaft that rotates. It's called a rotating disc electrode. And then you do electrochemistry on it. So, this is a cyclophotomegram in perchloric acid. So here what we're showing is actually we're cycling the potential. This is a cyclophotomegram in nitrogen. We're cycling the potential up and down. And so the positive current means you have an oxidation taking place, and the negative current means you have a reduction taking place. So actually, platinum 111 is the only surface, as far as I know, at least on platinum-based surfaces, where you actually have a very well-defined region where you have oxygen or OH absorbing, and region where hydrogen is absorbing. All other surfaces, you usually get a mixture of hydrogen and OH absorbing in the same region. This is contrary to popular belief. So what happens is, as you're cycling potential down, what you start to see hydrogen being absorbed, you get negative currents, and then it gets oxidized off. And then when you go into more positive potential, you get OH being absorbed and then it desorbs. And at least in platinum 111, you can see it's completely symmetrical. That means that it's at for example, hydrogen absorbs at the same potential as it desorbs. So it's that thermodynamic equilibrium. So there's no irreversibility, which is different from if you look at nanoparticles of platinum. You usually see that these peaks are somewhat asymmetrical. And so then when we put in oxygen into the cell, we start to see a current. You can see the current is a lot larger than it is here. So when we put, and this is because we've got oxygen reduction taking place. And so you start to see oxygen reduction reaction activity increasing, and then it flattens out here. That's because it's transport limited. And the reason there's an inflection here is you start to make hydrogen peroxide. So usually you make hydrogen peroxide in this region because you're covering the surface with hydrogen. It becomes more difficult to dissociate the oxygen-oxygen bond in this region. And so the potential losses for the reaction are shown here. So the difference between the red and the black line, and they're quite substantial, around, depending on the current density, let's say around about between 0.2 and 0.3 volts to get reasonable current density. And this is a problem for a fuel cell, of course, because it means you can't operate a fuel cell at maximum efficiency. So the question is, so if you look conversely at hydrogen oxidation, I haven't shown the data, you can actually catalyze the reaction with zero overpotential, even going through really, really large currents. So the question is, why do you have this really large overpotential? You'd much rather if it was like this ideal catalyst. So to actually understand this, then I turn to the work of my theorist collaborators, Jan Rossmeisel and Jens Nuskov. So what they've been doing, and Clotilde can explain better about the kind of theoretical methods next week, but what they typically do is they model they calculate the free energy of different absorbed species at the reaction, and they correct it for potential using what's called the computational hydrogen electrodes. So they simply look at the thermodynamics of each reaction step. And you can start to see kind of what the problem is already when we look at the simplified reaction mechanism. You have many different intermediates in the reaction, and you have to catalyze all these different sub-reactions at the same time. So you're going through OOH, OH to oxygen, oxygen to OH, OH to water. The problem is that they all bind via the oxygen atoms. They all bind in a similar way. So if you look at the free energy diagram for oxygen reduction, this is at the equilibrium potential. So you have, at the equilibrium potential, you have the same free energy of the initial reactants and final products. So then if you apply an overpotential, the whole reaction is downhill in free energy. So because there's 4 electrons in initial reactants relative to the final products, the actual change in free energy for this of the initial energy of the initial reactants relative to the final products is equal to 4 times the bias you apply. So on the ideal catalyst, you'd have a completely flat free energy profile going from this initial reactants to final products. Then you apply even a tiny overpotential, the whole reaction would be downhill, so you should be able to get large currents. However, it turns out that even on one of the best catalysts, which is platinum 111, which I already showed you the experimental polarization curve for, it turns out actually it's far from flat at the equilibrium potential. It's actually a bit corrugated. So there's two steps in particular, which are uphill. First going to OOH formation, and then this step is very downhill, and then this step here going from OH to water is very uphill as well. So actually it turns out this step is slightly bigger than this step. And to overcome this, you need to apply a bias equal in magnitude to this step. So it's about 0.5 electron volts, which is similar to the overall experimental overpotential. So it's only when the reaction is downhill you have really, really high current densities. So you can imagine actually, you could ideally find a better catalyst if you could maybe independently tune the binding energies of the different intermediates. So maybe you could actually stabilize the OOH intermediate and destabilize oxygen and OH. So, however, it turns out it's not possible to do that. As I already mentioned, they all bind via the oxygen atom. When they all bind by the oxygen atom, it means you can't tune each one independently of each other. It turns out, as it happens, they all bind, these intermediates, the binding energies of all of them scale linearly with each other, especially if you look like, say, for example, OOH binding. As a function of OH binding, there's a really linear correlation. There's also quite a good correlation between the oxygen binding and OH binding. So this constrains the reaction. It means that you can't change the binding energy of the intermediates independently. However, the good thing about this is it actually simplifies our analysis of the reaction. So this is the theoretical overpotential activity as a function of the binding energy of one of the intermediates, that's oxygen absorption. You could equally plot it as a function of OH absorption as well. And what you actually see is that even though it's complex reaction, you can actually describe the overall trends simply as a function of this binding energy. So if you look at a surface like gold, typically the problem of gold is it binds oxygen OH too weakly, and that it's limited by the activation of the oxygen. So it's more uphill to make OOH. Conversely, if you look for a catalyst like nickel, binds oxygen too strongly, and then it'll get poisoned by the reaction intermediate. So platinum is actually at the peak of the volcano, or close to the peak, not quite at the peak, simply because it has you have a kind of a better balance between the first step, going from oxygen to OH, and the OH to water. They're approximately equal in magnitude. When they're actually equal is at the peak of the volcano. So this is a quantitative version of the kind of the old principle proposed by Sabatier, who was a French chemical engineer working in America, who stated the most optimal catalyst for any given reaction should exhibit moderate binding to reaction intermediates, neither too strong nor too weak. However, this is a more quantitative version thanks to density functional theory calculations. So a lot of people have kind of semi-qualitative proofs of volcanoes. But we wanted to think, how can we actually make a kind of quantitative proof of it using well-defined surfaces, so we can really get see if it actually exists. Ideally, we do this on a single crystal surface, like the platinum 111 that I already mentioned. So just to recap what we'd expect to see, so this is resuming at the peak of the volcano, this is activity relative to platinum 111. So if you weaken the binding to OH, we should see improvements in activity. And if you go too far, it's less active. So you have usually you can do this in two ways. You can either just look at thermodynamic volcano. This is predicting what if there's no additional kinetic barriers, and purely based on thermodynamics, you'd expect to see maximum about 40 times improvement over platinum 111. But if you take into account full reaction kinetics, usually the enhancement's a bit lower. But this red trend is what we'd expect to see from experiments. This is what we want to set out and prove. So the way we decided we wanted to do that is using an effect known as the ligand effect. So this was an effect that had been studied a lot in theoretical calculations. So this is showing the oxygen binding energy for a number of different platinum surfaces, all with another metal in the second surface layer. So what you can see is that usually when you have a dissimilar metal, so this is platinum on one, if you put another metal in the second surface layer, you actually weaken the binding to both hydrogen and oxygen. This is called the ligand effect. A lot of people studied this in experiments, sorry, in theory, but not in experiments. But in my old research group, a lot of people have been looking and using ultra-high vacuum surface science. They've been looking at the ligand effect. Essentially what they've been doing is making what's known as a near-surface alloy. So they essentially physically deposited a copper overlayer onto a platinum surface, and then they annealed it in ultra-high vacuum, and then they did, and then they found that actually they could make it more noble, more inert. And they characterized using a lot of methods, including STM, and they could get nice broad terraces and a very ordered surface when they did this. They found, for example, when they tried to react it with carbon monoxide, it reacted much more interacted much more weakly with carbon monoxide than a pure platinum surface. And the total surface was platinum, and the copper was only in the second surface layer. And we actually decided, okay, we're using kind of, obviously, it's quite difficult to transfer samples from an ultra-high vacuum chamber to electrochemical cells. So we thought, how can we actually do this in a more, a less cumbersome way? So we decided, can we actually make this near-surface alloy using the methods we have in electrochemistry lab? So we just built a special cell to do this, where we essentially use what's called under potential deposition of copper onto platinum, where we just deposit around one layer of copper. Then we in the headspace above the electrolyte, we'd anneal the platinum single crystal in hydrogen. And this has a similar effect to actually having when you anneal the copper overlayer in ultra-high vacuum. Essentially what happens is that the copper goes into the second surface layer, and then you expose this platinum at the surface. And we could tell this was actually the case. We could, from angle-resolved X-ray photoelectron spectroscopy. So you can see its depth profile. So when we put the copper at the surface, we see copper is at the surface, and platinum is below. And then after annealing it in hydrogen, we see the copper is in the second surface layer. So this is exactly what we expected based on the previous ultra-high vacuum-based measurements of the surface. So now we've established a way to actually tailor platinum, and we think that it should be a lot more inert when you have the copper in the second surface layer. So now it gave us a toolbox to kind of play around with the reactivity of platinum. Particularly wanted to change, we expected that by changing the amount of copper in the second surface layer, we could tailor the reactivity to the reaction intermediates. So anyway, when we actually put the platinum into the electrochemical cell, with after depositing one monolayer of copper and then annealing a hydrogen, this is the result. So this is pure platinum, and this is platinum copper near surface alloy. So what you can actually see is that you require more positive potential to absorb OH. And if you had a completely homogeneous surface, the shift in the potential would be equal to the shift in the binding energy of OH, which is obviously the reaction intermediate for oxygen reduction. So this is a surface then we can actually directly compare to theoretical calculations. We think it was homogeneous because it's a single crystal surface. From the theoretical calculations, this is done by Federico Calle Vallejo. What he predicted is as you increase the amount of copper, then we would, relative to platinum 1, we would destabilize OH. So what I've shown here is when we put a full monolayer. So we expect if we put less, we'd see less destabilization of OH. You can shift the binding energy by changing the amount of copper in the second surface layer through this ligand effect. So anyway, we actually we changed the amount of copper we deposited, and then we annealed the platinum single crystal, and we actually found that we could actually see a shift in the OH in the voltammogram, which corresponded to a shift in the OH binding as a function of amounts of copper initially deposited. So this is shown here, and if you look at the black line first, this is showing the shift in the CV as a function of the amount of copper. We see more copper, more destabilized OHs. However, if you look at what the theoretical calculations suggested, that you should be able to see even stronger destabilization, especially when you put a lot of copper in the second surface layer. However, we didn't reach this regime predicted by the theoretical calculations. This was a bit disappointing. So anyway, we then had a look at, we also did some quantified amount of copper that was there using XPS, X-ray photoelectron spectroscopy, as a function of the amount of copper initially deposited. So, and this red line here shows how much we'd expect to see of the copper signal if all the copper initially deposited stayed in the second surface layer. And what we found is actually that when we put more than half a monolayer copper, we don't quite see some of the copper is missing. So we think that probably what's happening is you're fighting enthalpy and entropy, and that the enthalpy required to actually stabilize the copper in the second surface layer isn't quite enough when you're going to high amounts of copper, and you're losing out to the whole entropy of the massive platinum single crystal, so the copper is getting dissolved in the bulk of the platinum single crystal. And we did actually find, let's say if we annealed the single crystal in oxygen, we'd find copper would always come out of the single crystal, so it wasn't really getting lost in the single crystal. So in reality, actually, what we find from this is that actually there's pretty good agreement between experiments and theory, take into account that we're actually losing the copper. If you look at the shape of these two different figures. So we also went ahead and actually measured the oxygen reduction activity, and we found that we could see up to 8 times improvements relative to platinum 111. So it's really, really active surface, but if we put too much copper, we see lower activity. Now, actually, we've measured oxygen reduction activity, and we've also been able to tailor the binding energy and measure the binding energy, so we can actually make an experimental volcano. And this is what we found. We found it matches really, really well with the theory. We don't see quite the enhancement we expect. We also expect that from the theory. The main thing that we get from the theory is that we get a good trend. And it seems that so we both prove the theory and we show we can actually get a high increase in activity using this near surface alloy. So of course, you could argue this is just from our study. What about if we looked at other studies on platinum single crystals? And then we had to look, okay, what happens if we look at a simple platinum 111 single crystal? What happens if we look at other surfaces, more open surfaces? Generally, when you have undercoordinated sites, they tend to bind a lot stronger to reaction intermediates. So let's say if you look at platinum 211, the step site, what we find is that the theoretical overpotential is a lot larger. You'd expect much lower activity for oxygen reduction on the step sites than platinum 111. However, if you looked at the work of the group of Juan Feliu from Alicante, he'd actually done, and also Hoshi from Japan, they've been looking at platinum single crystals, and what they found actually is when you increase the step density, they actually see a modest improvement in activity relative to platinum 111. So it seems like the theory was completely wrong. So we had a closer look at their data. And what we found was actually, when we look at the CVs of these step surfaces, so here we've got platinum 111, And then here, this is when you introduce steps. What tends to happen is a shift. Sorry, the OH absorption peak in the CV tends to go to more positive potentials. And actually, what I think is actually this peak here is actually the OH binding at the step. And this is OH at the terraces. So it's true that when you have introduced a step, you bind OH a lot stronger. And that's the peak you see in this region, what's usually called the hydrogen under potential deposition region. I think it's probably not hydrogen. And then when you have, but you actually destabilize OH at the terraces. And this is very similar to the effect of alloying. So we quantified the shift in these different step surfaces. And what we found is that actually they all follow the same trend as the near surface alloy. We also put in the most active catalyst for oxygen reduction, which is platinum 3 nickel single crystal. So we think actually that this is pretty good experimental proof that this oxygen reduction volcano exists. So we're very excited about this, and also it's much more direct than other proofs in the literature, because we're actually measuring the OH binding energy in a very well-defined surface, and also measuring the activity on the same surface. Well, in alkaline media, so when we actually looked a lot of people suggesting, okay, in acid media the volcano exists, but in alkaline media it's actually completely different. So we thought, okay, this would be interesting to try the same setup a few years later in alkaline media instead. And what we did was actually so anyway, so this is a oxygen reduction reaction in base. And if you consider that you still have a proton-coupled electron transfer for every single step, if the binding energy of each of these intermediates should be the same as an acid. And the potential required to form each of these intermediates should be the same as well, at least on the reversible hydrogen electrode scale, so at the same overpotential. So, however, when we actually look at the data, we see quite big differences between acid and alkaline. So this is on gold 100. So in acid media, gold 100 is really inactive. There's very large overpotential. In alkaline media, it's a lot more active. So conversely, if you look at some other surfaces, so gold is a lot more active in alkaline media and less active in acid. And then also, if you look at platinum 3 nickel as well, so I already mentioned this very active surface in acid, and alkaline is even more active. It's really, there's an unprecedentedly high activity you see for platinum 3 nickel in alkaline media. And some people have proposed that some surfaces, especially like gold, are much more active in alkaline media because you have a slightly different reaction mechanism. You don't go through these proton-coupled electron transfers, you actually make a superoxide species. And when you go very alkaline, the superoxide species, the potential required to do that would be much more positive on the reversible hydrogen electrode scale. And this is maybe why relatively inert catalysts, because you overcome this initial step, which is a limiting step on gold. You can actually overcome this if you work in alkaline media. And talking to theorists about this, they always get a bit uneasy when you start to talk about what's a pH effect, because that requires going beyond just modeling surfaces in vacuum. You need to actually take into account the whole interface. And this, and particularly looking at barriers, is very challenging to calculate. I'm sure Clotilde will be talking more about that next week. So anyway, when we look at stepped surfaces in alkaline media, so this is actually showing the current oxygen reduction activity, as this is on platinum 101. As you introduce steps, as you go away from the platinum 101, what you find is actually see a lower activity. So this is the opposite of what happens in acid. So this is an example here on platinum 775, you see lower activity. So introduce under coordinates, nice, it's less active. And we actually looked, we thought, okay, maybe what's the reason? So we actually looked at the CV like before. We found the CV in alkaline media also showed a destabilization of the OH peak on a step surface. So we didn't really understand it. So what this would say, if you're looking at the trying to make experimental volcanoes, this is what we'd expect from theory. But we see that we actually see destabilization of OH, but we actually see lower activity than platinum-111. So it seems like Sabatier volcano doesn't actually work in alkaline media. So this is quite interesting. So anyway, so we went ahead. So this was from a student in Denmark, Kim Jensen. He actually put different amounts of copper and measured on a platinum single crystal and measured the OH binding. And just the same as an acid, we found that actually the more and more copper you put on the surface, the more destabilization of OH you get. So we then went on to actually try measuring platinum-111 in acid versus base. And one thing we found actually wasn't very well reported in the literature, surprising, even though this is a really well-known model surface. So even on platinum-111, there's quite a big difference between acid and alkaline. So if you look, let's say, in potassium hydroxide, you see a fourfold improvement in oxygen reduction activity. And then sodium hydroxide is somewhere in between. So changing the cation has just as much an effect as changing the pH from pH 1 to pH 13, which is kind of surprising to me. And so we tested oxygen reduction in alkaline media. This is in potassium hydroxide. And what we found is actually just the same as an acid. When we put in copper into the second surface layer, we see improvements in activity. More copper we put, the more improvements, and then eventually if we put too much copper, it's slightly lower. So we can actually measure the activity as a function of copper deposit, and we see a shallow maximum here. We see similar improvements in activity, about 8 times improvements to what we saw in acid. So this is what the results of the experiment. We also tried it in sodium hydroxide. We saw something similar. So then we also thought, okay, again, let's see what happens on other surfaces. So, as I mentioned previously, on gold, 100 is actually a lot more, it's very active in alkaline media and it's less active in base. So actually we had a look here actually at the CVs, and what we found is actually in acid, there's a destabilization of around 0.6 volts for the OH absorption peak on gold 1100 relative to platinum-111. But in alkaline media, there's only a destabilization of around 0.27 volts. So actually, in alkaline media, actually agrees better with a theoretical calculation. Theoretical DFT calculation suggests should be about 0.35 volts destabilization. I don't know what's happening in acid, but it seems in acid you're somehow preventing OH from being absorbed. I don't understand why that's the case. So co-plotting this data, what we find is actually including both our own data and also data from platinum-3 nickel in KOH and also and gold in KOH. We find we see nice experimental volcanoes. So it suggests actually, at least for these low index facets, so that facets which are not stepped, we see a good agreement between experiments and theory, and the Sabatier volcano exists. However, for stepped surfaces, in sodium hydroxide and potassium hydroxide here, they don't agree with the volcano model. So I think what I think is maybe there's some extra barriers for oxygen reduction when you introduce steps that can't be explained in terms of binding of intermediates. Maybe the orientation changes the barriers for proton transfer. And this is something that would be quite interesting to model using theoretical calculations. So to conclude this first part of the lecture, I've shown that what we did was we showed that using an effect that had been previously predicted from theory but not actually elucidated experimentally, a ligand effect, we could destabilize OH using a platinum copper near surface alloy. And the experimental proof of this, we use this to actually prove the Sabatier principle for oxygen reduction in both in acid media and alkaline media. Another thing is worth bearing in mind that oxygen reduction activity on these different surfaces is a lot lower in acids than it is in alkaline media, something that hadn't been reported before. I've seen a lot of papers saying that you always have higher activity in alkaline media. That's not the case for these surfaces. And there's a marked difference in alkaline media between the behavior of near-surface alloys, which all have 1-1-1 orientation, and step surfaces. So I think there's something else happening, some additional barriers on the step surfaces controlling reaction. But before going any further, I'm going to take maybe a 5-minute break. But if you have any questions, let me know. Are there any questions online? No. You have a question?
Like the monolayer of are you writing that from?
Yeah, so that's a good question. So the way we could figure out, I didn't go into much detail about it. So the way we could figure out how much copper we're putting on the surface. So we know we're using under potential deposition, so that means you absorb copper at a potential where you can't make bulk copper. And then so we put the copper on, then we stripped it off. So we can calibrate how much we put on that way. So using the charge, and then we just assume that charge we checked using XPS to see if the amount of copper was about what we thought it should be, and it was usually.
And also 1/6 monolayer integrate.
Yes, that's from integrating the charge as well. Yeah.
Acid and the alkaline media are different. Like have an influence on integration.
Yeah. So I mean, ideally, I haven't shown it here. So the what you'll find is, let's say, if you integrate these CVs, what you should do is you'll get you can estimate the coverage, and then there'll be a flat part. So it's like an absorption isotherm. There'll be a flat part where a wide flat part, and it doesn't really matter which point, exactly which point. Ideally, if it's behaving like a Langmuir isotherm, which point you integrate, if you know what I mean, because all the curves are parallel. But ideally, you go in the middle of the isotherm, so around 1/6 of monomer. But it's an approximation, right? So it's not ideal. And what we found, especially when we looked at some of these alloy surfaces, that the curves were not always parallel. But because that could be because of you have more long range effect, interactions between OH through a water layer, through co-absorbed water. But I think that yeah, but it's often better just to kind of take a simple model to try and understand it. I think the nice thing when you have a single crystal surface, it's very homogeneous, probably only have one type of OH, that's what we're hoping. But then when we look, this is difficult to do in a nanoparticle, because then you might have several different kinds of OH and several different crystal orientations. Well, you could hope that it would apply. That's why I think it's always nice to do the work. To understand things sometimes it's good to do it in a single crystal, because it does actually, it should be comparable to a DFT calculation. Other surfaces that could, in principle, work quite well. This is what we've been doing with Sylvia, for example, is trying to look at a single atom catalyst, and then it's also quite well defined. Are there any questions from online? No. So ideally what we'd like to do is to get this kind of agreement on a more kind of complex surface. But at least, because usually when you're looking at the DFT calculations, you have kind of, they make these periodic surfaces, and then that is kind of reassuring that there's good agreement. When we did this measurements in the surface alloy, we were hoping to get what we got, but we didn't actually know. So they did the DFT calculations before we did the experiments, and we were saying, oh, if we get a surface which showed a voltammetric shift of 0.1 volts, that's what we expect to see, the maximum activity, and that's what we got. So we're really excited when we got this data.
The theory as a guidance, you know, when you will be.
Yeah, exactly. But I'm going to show now, the next example I'm going to show is actually when we got a really exciting prediction from theory, and it was right for the wrong reasons. But sometimes it's nice when you see that something, when you see disagreement between experiments and theory, that's also something quite interesting, I think. Exactly, yeah. So, yeah. So you haven't taken into account all the facts. I'm repeating just so the people online can hear as well. Okay. So I'll continue now. So I'm going to be talking about, like I said, when we had a really exciting theoretical prediction, the catalyst would work well, and then in the end, it didn't. It worked well for completely different reasons. So this is the work we did on alloys and platinum and rare earths. So I've already shown you the oxygen reduction volcano. So this is showing, this is zoom in, looking at different platinum alloys. These are typical alloys you use in things like alloys you use in a fuel cell, like in the Toyota Mirai. You have platinum cobalt catalysts. And you can see that actually, so this is experimental activities, then kind of theoretical oxygen binding energy on a number of different surfaces from different groups. And you can see the overall trend follows quite well. I think it's not as convincing as my own data on the platinum copper near surface alloy, but it's still, because there we had experiments as a function of experiment, but it's still interesting anyway. So a lot of these surfaces, like platinum nickel and platinum cobalt, a problem when they're actually used in fuel cells, they work quite well initially, but they tend to de-alloy with time. So actually, working with Jeff Greeley, Heine Hansen, and Jan Rossmeister and Jens Nuskov, they did a screening of many different alloys, and they were trying to find what alloys could be less susceptible to de-alloying, have very negative alloying energies, the same with enthalpy of formation, and at the same time have the right oxygen binding energy. And this is the outputs of their screening study. Looked at many thousands of alloys all over platinum overlayers, similar to platinum copper near surface alloy I showed before. So this is, on the y-axis, they've got a descriptor for activity, which is oxygen binding. So they think this is pure platinum. They think the ideal activity should be around here. And the descriptor for stability, as I mentioned, was the alloying energy. So what you can see is actually many of the well-known alloys like platinum nickel and platinum cobalt have alloying energy, which is not particularly negative, which means it's not very stable. But alloys like platinum yttrium, platinum scandium, have very negative alloying energy. And that's because when you make an alloy with late transition metal and early transition metal, what tends to happen is that you end up having the D band exactly half full, half empty. So the bonding states are full and the anti-bonding states are empty. So on the basis of this diagram, two catalysts look really good to test. That's platinum yttrium and platinum scandium. This was one of the first tasks I did as a postdoc at Technical University of Denmark. We were very excited to do it. We tested electrochemically. We've already shown this in my lecture on kinetics. It's important to show to all of you in case to make sure we're on the same page. And what we found is actually we saw up to an order of magnitude improvements, particularly in the platinum yttrium catalyst. So the way we did this actually is important to mention. We took a 5 millimeter disc of the platinum alloy and measured it in rotating disc electrode setup. So we spatter cleaned it to make it clean, and then we tested it. So we were really, really excited. At first, I couldn't believe it when I got these data, and I didn't even want to tell Jens Nuskov because I thought he'd be too overexcited, and he was. And he didn't stop coming to my office for the next 6 months every day. So when are you going to finish the paper? So anyway, We also found other alloys of platinum and rare earths also really active, including platinum 5 yttrium, platinum 5 lanthanum. And we also made them in nanoparticle form, and we found it was really difficult to chemically synthesize them because platinum is really easy to reduce, and yttrium is not. So then, we tried to synthesize them chemically, and we failed, and it was really frustrating. So we thought, okay, we're in a physics department, so let's use a physical method. So we sputtered a target of platinum yttrium in the gas phase, and then we filtered out the right size and deposited it onto a planar surface. We had a very elaborate tool for doing this. And then we tested the activity of these nanoparticles. So this is a surface-specific activity as a function of particle size. This is a bulk surface, and this is nanoparticles. We can see this is for platinum, and here's for platinum gadolinium, platinum yttrium. We're going for larger nanoparticles. We start to see significant improvements in activity, but not for the smaller particles. And we see up to about 3 or 4 times improvement, especially for platinum gadolinium nanoparticles. So it showed it worked in nanoparticulate form, and it compared well with the state of the art at the time. Then we even found we could synthesize it chemically, but that was really a struggle to do that. We had to get everything very clean of oxygen, but we eventually made it, and other groups have done it as well and also seen improvements. Key question, of course, is why did they actually work? So we had a theoretical prediction, and that was for a very specific surface. And according to the theoretical predictions, this is a platinum yttrium. What expected was that you'd rely on a ligand effect. So you'd expect a lot of yttrium to be in the second surface layer, and you'd form a kind of this perfect single crystal type surface. And so there are 2 different effects which you could imagine you could actually use to weaken the binding of OH and oxygen. So apart from ligand effect, you also have strain effects. So essentially, strain effects is when you apply a compressive lateral strain onto the surface. For example, Peter Strasser showed this to be the case when you make a platinum copper nanoparticles. You have a very thick platinum layer. There's no ligand effect because you have a very thick layer, but because copper is smaller than platinum, there's a lateral compressive strain to the surface. And this weakens binding to oxygen. So the other effect is one I've already discussed, which is ligand effect. When you have, this is more short range. It's only from nearest neighbors of the platinum surface atoms. So this is when you have copper or another metal in the second surface layer. So originally expected, as I already mentioned, that this would only work if you have yttrium in the second surface layer, because actually yttrium is bigger than platinum. So we expected if we had pure strain effect for platinum yttrium alloys, we would actually make the catalyst less active, to go down the volcano, because you'd be pulling the catalyst apart. And we'd expect just a 1 monolayer thick platinum overlayer. So anyway, when we actually did electrochemistry, now we did the electrochemistry, we did a characterization both using angle resolved X-ray photoelectron spectroscopy and using TM, getting elemental map, but before and after electrochemistry. Before electrochemistry, we see the rare earth right by the surface, and after electrochemistry, we see a really thick layer of platinum. So there's no rare earth in the vicinity of the surface, suggesting that we had actually a strain effect, and we really couldn't explain this. This was perplexing for us. And then when we actually tried to look, so we thought add these kind of platinum 5 structure, because you imagine probably you have a strain effect. If you de-alloy a platinum 3 structure, you probably form an intermediate layer of platinum 5 structure. And we tried to look at these platinum 5 structures as X-ray diffraction. And it was a nightmare because to actually fit these data from XRD because there's so many peaks. And we found actually that the structure was really, really complex structure. So it's not a closely packed structure. It's very different from the theoretical structures. We have actually, one platinum layer and then 1 layer of the platinum and the rare earth. This one looks like a close packed layer, but it's not. And we have little holes above the rare earth. It's called the kagome structure from Japanese. And I asked theorists, actually, can you try and do a calculation? This is, they said the unit cell is too big. No, it's impossible to calculate. and they got annoyed with me, and they told me to stop harassing them. So it wasn't really, so we didn't really know what to do. So we thought, and also a lot of the theorists they found, especially for the some of the lanthanides, they're very difficult to model as well using DFT. So we thought, okay, the theorists have dropped us. We have to carry on doing experiments anyway. So the kind of picture we had was that you have a platinum rare earth surface, then you expose it to acid, and then you leach out the rare earth. And you have a thick, thick platinum overlay. So then we actually went to synchrotron in Stanford to try and understand what happened. And what we did, we actually made, back in Denmark, we made essentially something that resembled platinum alloy single crystal. We evaporated a lot of yttrium or gadolinium onto a platinum single crystal and annealed it. We had a really thick layer of the alloy. And then we measured what was, and then we exposed it to electrolyte and measured what was the structure we formed on top. So what we found, actually, is that to our surprise, even though we formed this complex structure that wasn't closely packed below, we found actually, we formed a crystalline platinum overlay on the top that was actually, did resemble closely packed platinum. And what we think is happening is essentially when you leach out this rare earth from this bulk structure, if you look here, it looks like you have something resembling a closely packed layer. So you can imagine if you have platinum layer on top of that, it would be like a closely packed layer, which is, and as it happens in this bulk structure, the distance between platinum is slightly smaller than a bulk platinum. So imagine if you had platinum overlay on top of that, it would be under slight compressive strain. Of course, we never measured the actual, we're only measuring the platinum distance in this overlay. We never measure that at the surface. To do that, we have to do STM. Actually, more recently, the group of Alexander Bandarenka have actually done that and found the platinum distance at the surface from STM was actually slightly compressed. So we also did XAFs of platinum gadolinium, platinum yttrium nanoparticles. And there we can actually measure the overall platinum distance and the overall nanoparticle, not necessarily at the surface, which is the catalytically active one, but we can still measure our overall strain. So here's the platinum nanoparticles, both before and after electrochemistry. We see that there's no difference in the platinum distance. Now here's when you have platinum gadolinium as prepared as a function of particle size. And then now we're going to show actually what happens after electrochemistry experiments. So what we see is actually for the smallest nanoparticles, the platinum distance is quite similar to the bulk platinum, but for larger nanoparticles, we see more compression. What we think is happening is that for the smaller nanoparticles, you're essentially leaching out almost all the rare earth, which is consistent with the TM images that we don't see much rare earth left, but for the larger nanoparticles, we still have a lot of rare earth left in the core. And another thing we found is actually we saw lower activity after stability tests, and this is also consistent with we saw further leaching of the rare earth. We think we have a thicker overlayer. So actually we can correlate specific activity relative to strain. So pure platinum yttrium, and on platinum gadolinium, and we see there's really nice correlation. So I think actually this is even when we're putting one after stability test, we're moving up and down the strong binding sides of the volcano. We never saw we actually reached the peak of the volcano, but we did see that by changing the activity, we see a strain. So this is what's interesting about this is that the effect we actually got predicted from theory was actually wrong, but we're doing kind of a lot of different. This is many years' work actually of characterization of the actual platinum. We eventually found the reason why we think it was active. And there was a compressive strain effect, which is counterintuitive because we expect the rare earth to impose tensile strain. Then we thought, okay, we've now looked at platinum yttrium, platinum gadolinium. What happens if we change the lanthanide atom? So and because we thought in particular this would be interesting because usually when you go further along lanthanides, you get the lanthanide becomes much smaller. So we thought maybe this would be a way of tailoring the activity. And this is work done by Maria Escribano, who's now at Copenhagen University. And we did this, we measured a lot of different platinum, polycrystalline platinum alloys. And what we found is actually, we see kind of like, we see as we're going through these different alloys, as we're going from smaller and smaller lattice parameters, meaning smaller and smaller platinum-platinum distance, we see improvements in activity, and it peaks around platinum terbium. So this looks like a volcano. We actually think it's not really a proper volcano, because what we found is what we think is actually happening is that when you're actually going too thick, that actually the strain kind of collapses, and you no longer have the same strain as when there's a mild strain on the surface. The more, if you think about it, the more strain you apply to the surface, the less stable it will be. So if you apply too much strain, it will collapse. So this is conclusion on the platinum rare earth alloys, part of my talk. That they were active and stable for oxygen reduction. We showed this both in extended surface and nanoparticles. I think the important thing to bear in mind is that the structure in the original DFT calculations was not actually stable. And this is really important to bear in mind, that you can, when you model, you can put a lot of unstable structures into a DFT calculation, and you can get what would be the activity. And but it doesn't always actually, that structure is not always what was actually formed under reaction conditions. So there's a lot of other uncertainties in DFT, but to my mind, this is one of the things that the biggest problems is that often when you have a structure that you have to take into account what was the actual experimentally active phase. And so I've had other predictions I'm not showing today. When we got predictions that the gold cadmium alloy would be really, really active for CO2 reduction. We actually found it was less active than gold, and it was really, really disappointing. And I think what was happening is actually the surface as predicted from theory was not actually stable. Even so, I think that it was still a really interesting line of work, and it attracted a lot of interest from industry as well, because I think that we essentially found through this kind of theoretical screening that a new class of platinum alloys for oxygen reduction, and we think that the kind of this it still hasn't been proven completely, but this negative alloy formation energy could provide long-term stability. The big challenge is to really synthesize a large scale and really test it in a device that requires a lot of optimization. Before going any further, does anyone have any questions about this part of the talk? Yeah.
All the shrinking factors change the demand
So so the question was, does the strain here? So it depends a little bit. Generally, yeah, compressive strain will shift the binding energy on all the sides. But I think it depends maybe on I think I remember seeing some studies suggesting when you have under-coordinated sites that it will go the other way. But this is on the terra side, but I'm not absolutely sure about that. But this work on the platinum rare earth, we had about 5 PhD students all looking at these, and about 3 or 4 postdocs. So there's a lot of, yeah. Are there any questions from online, Minan? How many people are online out of curiosity? Okay. So now I'm going to go on to talk about another kind of oxygen reduction, which is oxygen reduction to hydrogen peroxide. So just to give you a brief technological motivation, hydrogen peroxide is highly attractive as a kind of environmentally benign oxidizing agent. Its use is increasing, especially as chlorine is being phased out because chlorine is toxic. But it's usually made using an anthraquinone process, which is a batch process in very centralized locations. There's only about 50 or 60 in the world. Hydrogen peroxide is challenging to transport to high concentrations. There's been once there's a big lorry explosion outside the M25, whereas actually in many applications you only need a really small amount. You need about less than 0.1% concentration, which is usually sold at 30% concentration. So it would be great if actually you can make hydrogen peroxide electrolytically. Then you just need, using electricity, air, water, you can actually make hydrogen peroxide. You avoid reacting hydrogen and oxygen directly. It's a continuous process. And out you get, let's say if you put PEM electrolyzer, reducing oxygen at the cathode instead of making hydrogen, you submerge it in water, you get dilute hydrogen peroxide and pure water, because all the electrolytes is solid. However, you need a really selective, active, and stable catalyst for hydrogen peroxide. You don't want to make the more thermodynamically stable product, which you want to make in fuel cell, which is water. Another challenge is usually, so in alkaline media, hydrogen peroxide will decompose. It's better to make it in acid. And also the best membranes are in acid. And of course, in acid, you have less choice of materials. So, my first collaborators, Samir Sharastami and Jan Rosmas, were interested in making hydrogen peroxide. And what they proposed was that if so anyway, we were looking at the state of that. This is experimental activity as a function of theoretical, sorry, I'm getting confused, I'm tongue-tied now. This is experimental activity as a function of potential for hydrogen peroxide. And well, you can see the most active catalysts are gold, and palladium and gold also works quite well, similar to gold, slightly more selective than gold, and also nitrogen-doped carbon. This is work from actually Tim Fellinger and Marcus Antonietti there. But what we can see is actually, looking at the state of the art, the no catalyst actually could reduce oxygen to hydrogen peroxide at low overpotentials. So we thought, and our theoretical collaborators thought it should be possible to actually do this reaction, get what we'd call the ideal catalyst. So then Samir Sharastami and Jan Rosmas did some more DFT calculation, trying to elucidate what they could understand about the reaction on already known catalysts. So this is a free energy diagram for hydrogen peroxide production from oxygen. It's at the equilibrium potential. So the ideal catalyst have a complete flat free energy profile, as shown before, for 4 electron reduction. And what they could see is actually already known catalysts like gold or palladium gold is quite uphill to actually form the OOH intermediate, explaining why the activity isn't that good. So ideal catalyst will have this kind of moderate binding to OOH, and the already known catalysts are not actually in this region. But if you could get this ideal catalyst, you should be able to get high currents within close vicinity of the equilibrium potential. So, but the problem is, of course, is that as I already mentioned, you have a more thermodynamically stable product, and that's water. So this is actually showing the free energy diagram for platinum 111. I believe this is 0.9 volts, but I'm 0.7 volts. And then this is showing that actually, so on platinum 111, you actually, this is a free energy of hydrogen peroxide. It's actually much more downhill to form oxygen and then make water. So that's why it's showing why you end up making water, not hydrogen peroxide, on platinum 111. Gold 211, which is the theorist modeled as the active site for hydrogen peroxide production on gold. They see that actually, as I showed previously, there's uphill to form OOH, and there was still more downhill in free energy to form water, so you go via oxygen intermediate, than hydrogen peroxide, but it's less downhill. So this could explain why there's less driving force to make water than there is on platinum 111. So you can imagine, ideally, what you'd have is you'd actually, again, as I was suggesting earlier, you'd want to, in the ideal catalyst, you'd have more weak binding to oxygen, more weak binding to OH, and then you'd actually, especially to oxygen, if it's weaker than the free energy for making hydrogen peroxide, you'd actually be able to make a hydrogen peroxide selectively. So if this line here was up here. And then, so actually, but of course, because of the scaling relations which I already mentioned, this is actually quite difficult to change binding energy of intermediates independent of each other. So, and in fact, yeah, so you've got, this is a summary showing how the 4-electron volcano red intersects with the blue with the 2-electron volcano for hydrogen peroxide production. Now, the potential for hydrogen peroxide production is 0.7 volts. So it turns out actually, so I already mentioned palladium gold nanoparticles for a slightly higher selectivity. So then if you look at the similar activity to gold, so actually if you look at the free energy diagram for palladium gold, what you find actually is that there's less downhill to make oxygen, but the binding energy to OH is quite similar. So the binding energy of OH controls activity, but the selectivity, which would be the difference between oxygen and hydrogen peroxide, is much lower. So this means this could explain why it's more selective. And the reason for this is essentially you have, if you think on a pure metal surface, typically what happens is when you're going from OH to oxygen, OH binds to top sites and oxygen binds to hollow sites. And then, but however, if you on a palladium gold surface, what you'll have instead is that gold won't bind onto the oxygen won't bind onto hollow sites because it'll be coordinated by too much gold. It'll only bind to the palladium and it'll be forced to sit on top in a position where it's less stable. So you're kind of essentially destabilizing on this palladium, when you have surrounding by gold, you're destabilizing the oxygen without destabilizing OOH. So actually, some cobalt porphyrins show high selectivity for oxygen reduction, and they have a similar origin as well. So you can actually generalize this. So if you look here, metal and nitrogen-doped carbon. So this is so essentially the selectivity is controlled by the y-axis. So it's the difference between the binding of oxygen and hydrogen peroxide, the free energy of hydrogen peroxide. So if you're above this line, as you are for platinum single atom catalysts, you can actually selectively make hydrogen peroxide, and this on the x-axis is activity. So suggesting you can get better activity for the same binding energy on these single atom catalysts. But unfortunately, it also shows that activity and selectivity are correlated as well. So we thought, okay, what we want to do is to make a catalyst with the right binding energy to OH or OOH, so that would be around here, and also have a single atom configuration, or a reactive atom surrounded by more inert substrate. So looking at different alloys, people already tried gold alloys. We thought, okay, why not try actually mercury alloys? We thought mercury is very stable electrochemically, and it's very inert. A lot of electrochemistry in the past was done on mercury alloys. So we tested it. So sorry, we did the screened a lot of catalysts. A lot of them looked promising initially. Actually, pretty much none of them was stable. The only one that was really stable was platinum mercury alloy. And so essentially, the really nice thing about this was that we already found a detailed study where they elucidated the structure. So if you take a platinum single crystal, you and you electrodeposit mercury onto it. Because mercury is very mobile, you can make the self-organized crystalline structure at room temperature where you have isolated platinum sites surrounded by mercury. So in this case, usually when you're collaborating with theorists, they can actually propose lots of different structures and they're really difficult to make. But this one was actually really, really easy to make. To be honest, we actually found the structure before we did the DFT calculation. And we thought, let's put this in. And we actually did the experiment as fast as we did the DFT calculation, which was the first, because it usually goes the other way around. And so anyway, we took platinum single crystal, we also took nanoparticles, we deposited mercury onto them and tested for oxygen reduction. And we found there's actually, so we can measure, using what's called rotating ring disk electrode experiments, we can measure how much hydrogen peroxide. We could see that the amount of hydrogen peroxide being produced tracked the overall current for the reaction. And then when we found actually it was the same for nanoparticles as well. And then we actually found they were really, really active, much more active than what people reported previously. We also looked at a number of different alloys, like palladium mercury, copper mercury, gold, silver mercury. Found palladium mercury is even more active than platinum mercury. And when we plot the overall activity as a function of OH binding energy, we saw a reasonable agreement with theory as well, palladium mercury at the top here. So the nice thing about this, of course, is it all came a lot from the detailed interaction between theorists and experimentalists. And we ended up actually thinking, okay, this is a really nice idea. Why don't we set up a company to do this? And we ended up setting up a company to actually commercialize our invention. The only downside was what we realized when we spoke to people in the industry, so there's absolutely no way you're putting any mercury near the electrolyzer. Nobody wants to use mercury, but we've still proven that you could actually get really high activity and selectivity for hydrogen peroxide without compromising. You get high selectivity without compromising in activity. So we later found we could do this in other materials as well. And we're now selling these hydrogen peroxide units in 15 different countries. This isn't a direct impact of kind of a collaboration between experiments and theory. So I think it's quite interesting that really you could probably, this is an example where you could actually use electrochemistry, especially as electricity is becoming cheaper and cheaper. You can actually use electricity to actually make a localized production of our most coveted chemicals. Now for the last part of my talk. Does anyone have any questions about the hydrogen peroxide part, by the way?
I have a question. When you mentioned all these nitrogen carbons, when you look at the reports in literature, it doesn't really seem to be a correlation between the metal center and the selectivity to hydrogen peroxide.
So so you're asking why is there no correlation between the metal center and activity? There could be a number of reasons for that. One could be the DFT got it wrong. The other thing could be, one thing to bear in mind, actually, what we found, I didn't explain this now, is that it depends a lot on the mesoscopic structure as well. So the thing is, if you have, so if you think about here, as I mentioned previously, probably what's controlling selectivity is the difference between oxygen binding energy and the free energy of hydrogen peroxide. The free energy of hydrogen peroxide depends on the concentration of hydrogen peroxide. So we found that actually a lot of the catalysts are most, so imagine if you have a very open structure, then hydrogen peroxide will get away from it very fast. It might have a higher selectivity than if you have a very narrow pores, for example. So that could be, I mean, that was a nice thing about, again, nice thing about doing it on a model surface, a planar surface, then we don't have those effects. But obviously, a real surface is 3D. So then I think usually the way I think about it is a model surface is usually something you can aspire to on a real three-dimensional surface. But in some cases, it's difficult to synthesize some moieties on a two-dimensional surface. That tells you what you could expect if you optimized everything really well. What we usually found as well when we did actually try these platinum mercury alloys in a real device, we found the selectivity was much worse than rotating disk electrode experiment, because we think that the mass transport of the hydrogen peroxide is much worse than we've got much higher current densities, but we end up going for much more inert catalysts like carbon, and kind of having to tolerate high overpotential to get maximum current density, maximum selectivity. So moving forward, so I'm going to finally talk about the last part of my talk, and that's something we're researching a lot right now here at Imperial. So that's a nitrogen reduction to ammonia. So current production of ammonia via Haber-Bosch, very much like hydrogen peroxide is done in very centralized locations, and ammonia is a real pain to transport. And also, usually ammonia then converts into nitrates. A huge amount of nitrates actually are not wasted, and it causes a lot of pollution to the environment. It's a really big problem. And apart from that, the hydrogen usually from a Haber-Bosch process comes from natural gas, which is makes enormous amounts of CO2. So it'd be great if you can actually make ammonia via electrolysis. You can be powered by renewable electricity. You can make on-site, on-demand fertilizer production. You even use ammonia as a sustainable carbon-free fuel. And really the key to it is the catalyst shown in the inset, and actually no catalyst works well today. However, if you look at adjacent fields of homogeneous catalysis, you find that actually nitrogen can be reduced to ammonia with reasonable selectivity. And nitrogenase also works well, all at room temperature. So it'd be great if you could actually emulate nitrogenase on a other inorganic solid surface. So ideally what we do, and do the same as we were doing oxygen reduction, is we take a metal surface and put it into an aqueous electrolyte. This would be great if you could do that for nitrogen reduction. This is what we're very accustomed to doing. However, what tends to happen is that nitrogen is really inert, protons are really reactive. Protons will, and the reducing potential form absorbs hydrogen, shown here, and then you end up blocking the surface, and you can't reduce nitrogen to ammonia. So, and actually, so I had a chat with theorist collaborator Alexander Baga, who's actually really excited. He's going to be coming to Imperial this spring for at least a year, if not 2 years. And I said, what's special about a nitrogenase? Why can nitrogenase work, and why can't metal surfaces work? He said, okay, I'll do some DFT calculations to try and see, is it something special about the catalyst? The answer, an answer is actually no. So if you look here, so this is a nitrogen binding energy, that's a function of hydrogen binding. So if you had a really, really selective catalyst that could work in principle in an aqueous solution, what would happen? It would bind nitrogen. It would bind nitrogen really strongly and hydrogen weakly. So it would be in this quadrant here. Well, what we can actually see is that no surface actually is in this quadrant. Not metals, not metal doped carbons, not even lithium mediated structures, which we found actually work experimentally. So all the catalysts either up here, so things like gold, they bind nitrogen and hydrogen weakly. This region that they bind hydrogen weakly and nitrogen weakly, or in this region, even nitrogenase, it binds nitrogen. So nature's catalyst for nitrogen reduction binds nitrogen strongly, and it binds hydrogen strongly. So this means that to circumvent this, nature's found another way, and you have to go beyond just solely looking at the actual at the catalyst material. You actually need to tailor the environment. It turns out it has a hydrophobic environment around it. So we need to, nitrogen reduction is a little bit more hard, simply because nitrogen is so inert. However, so in my old research group, who were looking at this a lot, we found a lot of reports in the literature who are putatively reducing nitrogen to ammonia, And we were getting quite frustrated because they were saying that they were able to achieve things we'd never able to achieve. They were able to reduce nitrogen to ammonia, even on very inert surfaces like gold. I showed in the previous slide, gold shouldn't work. And even on platinum, they found they were able to make nitrogen to ammonia very close to the equilibrium potential, which are about 0 volts. We could not reproduce any of these data. So if you have a closer look, actually, even a lot of studies, and this is, I'm taking one example here, but this is actually really common. So they're showing that they're making ammonia very close to equilibrium potential, around minus 0.2 volts. And even though, if you look at the free energy diagram, you're seeing that it's actually 2 electron volts uphill to actually make the first intermediates in nitrogen reduction. So actually, we did a calculation in a review paper that a few of us put together last year, including Jesus, who's in the audience. We found that actually for free energy barrier of 2 electron volts, and if you might apply a 0.2 volts over potential, that you'll get a turnover frequency of around 10 to the minus 16 molecules per second per site being formed. So typical turnover frequencies are on the order of around 1 molecule per second per site. That means there's absolutely no way, if you have this gold nanoparticle, that you'd be able to reduce nitrogen to ammonia. So it's worth bearing in mind, even if you take into account that DFT has a lot of uncertainty, maybe 0.2 electron volts, 0.5 electron volts, there's absolutely no way this would work. So actually, and I've seen tons and tons of papers like this suggesting that they can reduce nitrogen to ammonia, and they show, even in their own studies, showed the free energy diagram proves it doesn't work. So this is actually really useful to see how, because obviously, as an experimentalist, if you have lots and lots of data which you don't really trust, at least theory can do an experiment that will never work and explain to you why it doesn't work. Because you have negative experimental results, it's often difficult to explain. So we actually looked in more detail, and we found the only thing that really worked was, we found actually, if you look at these, motivated by this theory suggestion shouldn't work, we found actually, unsurprisingly, a lot of these studies reporting nitrogen reduction to ammonia were actually looking at really, really low amounts on the order of parts per million. And I think they were basically looking at contamination. I won't go into too much detail. We found the lithium-mediated structure actually worked. And I think the reason for this, based on the DFT, is that actually we're models, is that we're actually restricting access to protons using what's called, battery scientists would call the solid electrolyte interface. So summarizing all the different structures, I think that we know from DFT that we need something that can activate nitrogen. So all the ones that actually work have some things like iron or lithium or molybdenum at the active site because they're very reactive metals that bind nitrogen, but they have constrained access to protons and constrained access to electrons to minimize, to prevent absorption of hydrogen. And this brings me to the end of the part about ammonia. So what I would say is that theory is far ahead of experiments. For nitrogen reduction experiments, almost 99% of the experimental studies are based on false positives, but it is changing, luckily. And there's a scaling between hydrogen and nitrogen. So tailoring catalyst material alone is insufficient to drive nitrogen reduction. This is something we found from collaboration with theorists. And I think what's nice about this is DFT can really serve as an excellent reality check on bogus experimental data. So to conclude my talk, I think collaborating with theorists, what's important to do is to be open. So I think you have to admit experiments can be wrong. You need to build trust, you need to meet regularly and for extended time periods. Of course, it's difficult sometimes, especially in the past 2 years when we've been all locked away at home. And what I found is the strength of collaboration is inversely proportional to log of the distance. So we found that actually, so I knew this from because I was working with a theorist in Denmark, and I initially started in the same corridor, and then we went to the same building but a different floor. And there was quite a big difference between not being in the same floor. And then when we found that actually in this, and then some of them moved to Stanford and some moved to Copenhagen University, which is a few kilometers away. And there wasn't that much difference between them being in Stanford or in Copenhagen University. So I think proximity is important, if not lots of Zoom calls. I think it's important to distinguish what's actually certain, what's uncertain. So individual data points are usually are not that important from the theoretical calculations, but it's more important the trend, because usually the trends are quite robust, but the individual point, let's say where one catalyst is on the volcano, is not always that robust, especially for certain systems. So usually, let's say, if you're just all you're changing is changing composition, keeping the same surface orientation, trends should be more easy to calculate than between different surface orientations or between very different classes of catalysts. Let's say if you want to compare enzymes and metals, let's say. I think the effect of solvation on binding intermediates is very difficult to account for, and also charge transfer barriers are particularly challenging to model. This is something that Clotilde will talk about more next week. So I think close comparison between experiments and theory can answer open questions. So for example, I showed you could provide answers when steps improve oxygen reduction activity. And we found out just by looking at experiments, we seem to decrease OH binding on adjacent terraces. But it could also open new questions, like why is step platinum gold so inactive for oxygen reduction? I think the other thing that's really important to bear in mind is the structure formed under reaction conditions is often really challenging to predict a priori. You have to really push your theoretical collaborators if they want to do it. And then the theoretical screening might lead to high activity for the wrong reasons. You need to use well-defined surfaces often. So we did, as I mentioned, we made a single crystal platinum yttrium gadolinium. And finally, using an example of nitrogen reduction, theory can, especially for an area which is not very well developed experimentally, theory can provide a reality check on flawed experimental data. So looking forward, of course, all the examples I've shown have really been on very well-defined surfaces. We're looking at doing very careful low throughput experiments. We also have the question is when you see, and often actually the conditions are very far from real devices. So you always have the question, have I just got a good correlation because I've been looking at a really limited range of data and because I really wanted it to work and it ended up working out? Could we see more general trends? I think there are developments that are going on, so that I think we're at least Imperial with a lot of people like Camille Petit and Magda Tisrici are very interested in doing automated chemistry. So then, usually, especially when you want to make a real device, there's so many different steps and so much optimization that it's very difficult to look at new materials. But if you could have a robot to do everything, it'd be a lot easier and you can get a lot more data. And then in parallel, there's a lot of developments in machine learning. And this can actually offer new opportunities for actually kind of both making predictions and also analyzing experimental data. So you can imagine really going through more, rather than kind of an iterative loop with many stops in it, going through a continuous loop where you're actually making experiments and getting a lot of materials and then using the same data. It's using kind of big data approach to analyzing all the data. And so ideally what we'd like to do is to probe a large number of electromaterials at once under conditions resembling real electrolytes, and then analyzing all the data, maybe doing in situ spectroscopy. This is something we're trying to do and working with Camille Petit and Magda Tisrici and James Darrant and Clotilde Cucinotta and Aaron Walsh. I'm sure I've forgotten some people. Anthony Kustanak. We're trying to. This is what we're going to try and do for water electrolysis, and also I know Magda and Sam Cooper and Mary Ryan and I are also interested in doing it for batteries as well. And eventually, we can maybe get even more insightful correlations and understanding by combining experiments and theory. Okay. This brings me to the end of my talk. I'll be delighted to answer any questions. So if anyone has any questions online, let me know. You can overwrite it or speak out if you like. I guess Jesus and Hoye and Mina, you're more familiar with this stuff in nitrogen reduction. Oh, maybe he wants to write what about something. Well,
is the DFT like a reliable when you modeling nanoparticles?
so I think it depends. I think often there's a lot of debate about this, but I think that it depends on the nanoparticle. And what we found, for example, with the platinum alloys, there's pretty good agreement between what we found in single crystals and polycrystalline stuffs and nanoparticles. When you get down to it, I guess some structures that I think probably locally, I think it can work well. So it just depends on what you on the specific nanoparticle. Yeah. I mean, I guess it depends a bit. Yeah, it depends a little bit as well on what structure you're looking at. Let's say, for example, for oxides, working with Reshma Rao, we found from single crystal, we got really nice kind of agreements between experiments and theory. But when we look at the nanoparticles, we have no idea. Often it's even the idea of what the active site is a bit more vague. There could be, because we don't know what surfaces are there, and actually they're also very difficult to model from a theoretical point of view as well. So I think usually, kind of like what I said before, when you're looking at the very broad trends, it works. And if you see a huge difference between two different surfaces, then probably it's not that sensitive to the model. But if you're looking on the order of 0.05 electron volts, 0.1 electron volts differences, then it makes a big difference. I think that, and it depends on the reaction you're looking at. So I've been showing mainly today about oxygen reduction, and it's more straightforward than it is, let's say, for CO2 reduction or glycerol oxidation when you have many different products. And it's actually also difficult to measure experimentally, right? So which experimental data do you use to kind of configure it? And let's say that, I guess, in some ways, if you're starting off on a model, the ideal, let's say, if you're working with their ideal surface to kind of to compare to is a single crystal surface. And if it doesn't agree on a single crystal surface, then you wouldn't expect it to agree on a nanoparticle. But if it agrees on a single crystal surface, then you might expect it to work on a nanoparticle. But ideally, yeah, we'd be trying to look at to get more. I mean, another way you could do it in the future, you can imagine doing kind of a more big data approach, doing lots of experiments with not quite the same accuracy, whether you'd be measuring, let's say, doing a lot of spectroscopy. And the problem is, if you're only measuring activity all the time, the problem is you're measuring current as a function of potential. There could be loads of different reasons why you have high activity. But if you could do some other check, like doing kind of in situ spectroscopy or something like that, to see why it works, then that gives, or changing some other parameters. And if you have multiple correlations all agreeing with theory, then it's more convincing than a single correlation.
We have a question online.
Yeah.
There's a question from it asks, what sort of catalyst for upscaling ammonia production or storage would you tackle first? And how are you planning to assemble or change the cells?
So what's the one? So I guess for ammonia production, the only one that works right now for electrochemistry is lithium. If you upscale anything else, even if you put 1,000 times, a million times of a million electrolyzers of gold, you'll still make zero ammonia. So I think that the only one you could think about upscaling was a lithium one right now. And there are some people actually trying to do that. But the only problem with lithium is that you're limited because you have to go to very negative potentials. So maximum efficiency is limited to about 30%. And so what was the second question?
Like how are you planning to assemble or treat cells?
This is a good question. We don't know yet. But even for the automated approach, kind of, yeah. So that I think that what we'd like to do is make a cell that's relatively straightforward to make, but at least we can. The idea was that you can make synthesize, having a robot to both synthesize the material and assemble electrodes, and ideally test them all at once. Obviously, the robot might not be as versatile as a human in terms of synthesis methods, but it might. But I guess you're taking out a lot of reproducibility. But you have to choose kind of a synthesis method that can match the robot. But at least you have to be very versatile of that. You'll be able to do a lot of different, change a lot of different parameters in the controlled way with that. And ultimately, probably as you develop more and more sophisticated robots, you'll be able to get robots that can do more complicated synthesis methods. No, but I know, for example, even in my own spin-out company, we got the biggest irreproducibility we found was actually when we were trying to make hydrogen peroxide was the brushing of the kind of the deposition of the catalyst, and we because with tons when we would get everything working really well in rotating disk, and then everything was working for like a month, and then suddenly it stopped working. And then we figured out that we checked because someone was complaining because we got carbon black everywhere. So we had to do the deposition inside a glove bag. And it was at that point everything stopped. So then actually we got a robot to make to spray everything, and then everything started working a lot better. And that's just for one step. So imagine if you could do every step of a robot, it would be really good. And much easier to compare to a lot of theoretical data.
Yeah.
But we have robotic spray actually here. I think Jane Nelson and Anthony Kustanek have one. We just need a lot of it, yeah. We need a lot of catalysts. So, any more questions? Okay, so thank you for everyone for listening. Thank you for those coming in person. So hope for next week for Clotilda's presentation, we'll have more people coming in person as well. But thank you to those who did. Appreciate it. But okay, thank you.